I hear myself in a very annoying way, but never mind. This is joint work with Markus Lepper from Berlin. And it just occurred to me last night that this talk is in sonata form, but that's a different matter. Right. What I'm going to talk about, that might help. Oh yes, thank you. Is a synchronous functional data flow language called SIG, which we have been developing for a few years now, which is similar in spirit to functional reactive programming, but not quite the same thing. So if you ask me again about the details, it's very difficult to tell how to compare the approaches actually, because we simply started from scratch and didn't mind what the FRP people were doing. There are a few new features in SIG that have been developed in the last year, and I'm going to show these new features using a classical description of an interesting sound, which is interesting from the psychological perspective, but also from the sound synthesis perspective, because it's a very small problem, but it's not non-trivial for programming approaches. And it happens that this is the ideal application to show the new features in a nutshell. Okay, so what's this SIG language about? It's a total functional language. There are no side effects, no spontaneous events, no recursive functions. It's a data flow language, so control flow is only implicit by data dependency of operations. So there are very few things to shoot yourself in the foot, but variables change over time. They are clocked synchronous signals, so essentially every variable is a data stream, and all streams are updated simultaneously. The SIG language has an execution model that is fit for real time. It's a pull-based model with ultra-low latency. We heard this morning about latency problems with push-based thread-oriented approaches. This one is different. And our intended applications for the language are embedded control software, scientific simulations, and of course, audio demonstrations. That's why I'm here. Right now, the SIG language compiles to the Java virtual machine, but we're also planning C backend. We want to compile to digital signal processors and also to FPGAs. The design of SIG is organized into several layers. There's a call language that has very simple compositional semantics. It's essentially a structured approach to melee automata. And then there's a functional front-end language with cherished things like algebraic data types and pattern matching, and also higher-order functional programming. That's one of the new features I'm going to talk about here. And then there are some other advanced things like a type system with physical units. That's a different story, and multi-rate systems, where synchronous doesn't mean that all the streams are updated at the same rate, but there may be different rates coexisting in a system, and that's the second feature I'm going to talk about here. And the idea is that the higher layers of the language are boiled down to the core language, but by some sort of program transformation. Here's a very basic example of how this language works. If you look at this component, it takes an input stream X to an output stream S, and the value of S is defined as initially 0, and then the semicolon is a single-step delay. So after the first element, which is 0, you have a delayed copy of the expression S plus X. And this one looks very similar, sends X to S. And here, S is the sum of X and some expression that's initially 0, followed by a delayed copy of S. And if we forget about the initial values for a moment, then these are the data flow diagrams. So you have a sum and a single-step delay operation, and just the wiring is a little different. And now we transform this to the transition function of a melee machine. For every delay operation, we introduce a pair of pre- and post-state variables. And then the delay operation simply sends its input to the post state, and its pre-state to the output. So then the diagram looks like this. Sorry for the complicated wiring. You can pull on this thing, and then you see that this one sums the input X and the anonymous pre-state and sends a copy of the pre-state to the output and the sum to the post-state. And then the stream semantics of this diagram is obtained by replicating this thing omega times and plugging in the initial value here. Then we end up with this diagram. So in this case, the first output element is 0, and the second output element is the sum of 0 and the first input element, and so on. And if you stare at these things for a while, you can do equational reasoning and come up with the formula. So the nth element of the output is the sum of the preceding elements of the input, n exclusive or n inclusive here. So that's the basic idea of how the core level of this language is supposed to work. And you see the semantics are very simple, and that's important because we really want domain experts, control engineers, and musicians to be able to understand the formal semantics of the language. Now, the application we're using, is the so-called Shepard Tone. The Shepard Tone was invented as an acoustic illusion to create the impression of different movements in pitch on the short and on the long time scale. So it's sort of an auditory strange loop, something like this famous Escher picture, or more accurately like staring at a barber pole. It's a fairly small problem that can be described in a few minutes, but it's non-trivial. So if you try really to synthesize sound from scratch, it can be quite hard. And the full SIG code is in the paper. It's about 1/3 of a page, and there's a long discussion of every detail. The general idea is like this. You have every thick line here is a voice. So you have several voices. They are spaced at some harmonic interval so that the sounds sort of fuse into one composite sound. And they all move linearly through the pitch space. Usually they're all going up. And unfortunately, it's not possible just to record a clip like this and play it in a loop, because in order for the effect to work out, if this point is simply repeated here, then the phases don't match. So the oscillator that comes from here, this voice, and the voice that's repeated up here, they don't line up in the phase, and then you can hear a click. And it's numerically impossible to get rid of this effect, so you really have to model the individual oscillators and switch them on at some point in time and switch them off later. And finally, to make the illusion, these events where voices are switched on and off are made imperceptible by fading each voice in as it starts at the bottom, and then having some maximum volume in the middle, and then fading it out towards the upper end of the pitch range. Okay. And in order to express this naturally in a programming language, we added two things to the SIG language. The first is high-order programming. Well, of course, a high-order functional programming language is much more fun to use than a first-order one. But it's known to be a tricky problem to combine high-order functions with streams. So you have to explain what is a stream of functions, of streams to streams, and so on. And there's a guy in the audience who has thought about the theory for a long time. Unfortunately, his solution doesn't quite work in our case for some technical reasons. So we had to come up with something different. And there is a problem. So we cannot do this naively, because in SIG, every variable is a stream. So when you write down a function, it's actually a stream of functions. And all the streams are synchronized. If there is a data flow dependency, then they're synchronized. And now let's look at an example. So this is a very simple component that has two inputs, and the output is just the sum of the two. And obviously, you want this thing to be synchronized. So every element of the output stream should be the sum of the corresponding elements of the input streams. And when you apply currying now and turn this into a higher-order function, then you get something very strange. You get a component that turns a stream of values into a stream of functions, and each of these functions, in turn, takes a second value and produces a sum. But if you map an input element to a function, then you expect this function to shift the second value y by the element of x that is bound. So if you look at this thing, then every element of the output stream of functions should be a stream function that sends the current element of y plus the sum of the element of x at the time that f was created to the output. And so synchronization has to be broken here. Otherwise, you can apply each of these functions only once. And what we did is we looked at that technique called staged metaprogramming, which is the idea of enriching a functional programming language with operators for explicit control over evaluation order. Usually it comes with 3 operators. There's a suspend operator that defers computation, so creates a piece of code that is only to be evaluated at the next stage of the program. Then there is an operation called splice that escapes a subcomputation from a suspension. So it's evaluated at creation time before the suspension is evaluated at a later stage. And finally, there's a run operation that takes suspended code and runs it, of course. The idea is very, very similar to Lisp quasi-quotation. So there you have backtick for suspend, you have comma for splice, and you have the eval function. The difference is that the staging operators by construction are strongly hygienic. They always refer to variables bound in the lexical scope and don't create any strange effects. And usually they're also reflected in a type system. There's also a similarity between stage metaprogramming and partial evaluation. You can think of offline partial evaluation as having a first part binding time analysis that turns any program into a 2-stage program, and then you have a specialization phase that runs the first stage of this 2-stage program, and the second stage is the residual program that you get back. A couple of years ago, people have considered of using staged metaprogramming to adapt high-performance programs to their runtime systems. In SIG, we introduced the 3 operators for staging, and these were the ASCII symbols that hadn't been used before, so that's our staging operators now. And the rule is that you cannot just suspend arbitrary code in SIG, so it's a simplified version, but every local anonymous function is suspended. And suspension freezes time. So if there's a free variable in the suspension, then it doesn't refer to a stream. That's what causes synchronization problems. But it refers to a constant, a single value of the stream at the time of suspension. And now if we look at this example with a suspension operator here, then every element of the stream of functions f binds the corresponding element of the stream of numbers x at this point, and then we get the intended semantics. Okay, the second feature is multi-rate stream programming. In audio systems, usually parts of the system operate at different rates. So you have audio rate, the rate at which samples of the waveform are produced. That's usually something like 44 kilohertz for CD audio, but can be higher in studio applications. Then most of the practical systems have something like a control rate at which parameters are computed there that are so computationally expensive that you don't want to do it on every sample. That's usually something like a fixed power of 2 slower than the audio rate, or in other systems it's fixed at something like 1 kilohertz. Then there are rates at which certain events can happen. In the MIDI, real-time MIDI, there's something like a beat that's 24 signals per quarter note. So you can have triplets and so on. And if you think of techno music, there you have this duns, 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 beat of exactly 2 hertz usually. And you can think of initialization of a complex system as part of the computation that operates at rate 0. And then you have asynchronous data flow between the subsystems of different rates. So from slow parts of the system to fast parts of the system usually have flow of parameter values. That's called modulation. And the other way, you have some statistics like volume peaks or energy balance or something that's aggregated at the fast level and propagated back to the slow level for filter feedback and so on. And finally, when you have higher order programming, you can also have components, functions flow from the slow parts of the system to the fast and reconfigure things while you go. Here's a very simple example of how things look like in SIG. There's a component that just adds the element of x to y, starts with 0, and multiplies each x with a constant dt. So in SIG, there's nothing in the program that specifies at which rate this component is to be run. That's up to the usage context to decide. So every component can be reused at different rates. But this constant dt is instantiated to, well, the inverse of the rate that it's actually running for real-time computation. And data flow by default is synchronous. Everything that's connected by a primitive operation operates at the same rate. So x and y have to operate at the same rate because they appear in this arithmetic expression together. So for a system, you get a set of rate equations. And if there are independent subsystems, then these independent subsystems can operate at different rates. Well, that's trivial because then there cannot be any interaction between them. But you can have exceptions. You can have asynchronous data flow by adding resampling operations. So if you have a signal and you apply an upsampling operation, then you get a copy of the signal, but at a higher rate with values repeated, and you get a rate inequation. Or you can, repeat every value of the signal 5 times, then you get a rate that's 5 times the input rate. Now, look at this example. This is an oscillator. It has an audio signal output here. And this is amplitude times the sine of the phase, of course. And the phase starts with 0 and then progresses linearly according to some frequency, or rather angular velocity. And now let's say we want to modulate the amplitude and keep the frequency fixed. Then we add a suspension here. The frequency is a free variable of the suspension, so it's fixed. And the amplitude is an input, and this input is upsampled. So it can come from a signal with a lower rate. Then next we do static analysis of the rates for the variables in the system, and we find that, of course, the amplitude rate must be less or equal to the rate of phase and out, which are synchronized. And then, when the analysis is done, we slice the program, this component, into the synchronous parts. So for this component, we get this part, which just consumes the amplitude and does nothing visibly, operating at R1, and this part, which uses the amplitude and does the rest of the computation at the higher rate R2. And the data flow happens magically behind the scenes by some sort of asynchronous buffer. So amp minus and amp plus are just the writer and the reader side of a single value buffer, and it's of course possible to read at a faster rate than you write. This is hidden from the user, and then there are some well-defined scheduling rules that keep you from nasty surprises and race conditions. Okay, so how do we do this Shepard thing? I'll give you the audio demo first. So this is a live sound synthesis program. I guess you get the impression. That was Shepard's original idea, to have discrete steps, something like a semitone in this example. And then later on it was refined. That's more complicated. And now we do the pitch steps at a rate that cannot be resolved by the ear anymore, and then you get something like this. Okay. The program is very, very simple in its architecture. There are three tiers that more or less correspond to the three rates: audio rate, the pitch step rate, and the switching rate of oscillators. Every tier has two stages, one for configuration and one for running the actual loop. The code is not quite trivial because there's all the technical details of a real programming language. It's 27 lines in the paper, and we use some primitives there that cannot be discussed right now. The general idea is the top tier is the ensemble of voices. So that's an array of live voices. These voices are functions. They are sample generators, and they shift at some rate through this array, and one is shifted out and a new one is shifted in at the bottom, and the outputs are mixed together for every audio sample. So you can see some operation here that creates an array. You have a shift operation over there, and then the whole thing is somehow summed over. So that's about the amount of detail that I want to discuss. Then the second tier, every voice has an oscillator and modulates the amplitude and the frequency of that oscillator. The pitch increases linearly, and it's run at some faster rate that's obtained by subdividing the clock of the switching events into steps. For the first one, I used 12 steps for every octave, and now I'm using something like 1200. And finally, the oscillator that's controlled by a voice just maintains the phase continuity so that there is no audible click. And the waveform that turns phase into audio signal, and the envelope that turns pitch into amplitude, they are function value parameters of the whole system, so they can be replaced on the fly if you like. And the audio rate is driven by the external real-time sound system. So you have the frequency and the amplitude here, and they are upsampled to audio rate, and then there's the real-time component here, and the waveform is invoked, and then you get a sample. Okay. What you've seen is, what you've heard, is not actually an automatically compiled SIG program yet. I'm very sorry about that. We have this textual front-end language. Most of the features compile to Java virtual machine bytecode. Algebraic data types and so on, that's all working. Staged higher order programming works. The runtime environment is very much complete, including the multi-rate components, but the static analysis of rates is not. So I had to cheat, to simulate the code generator by hand, but the program that you heard was programmed against the actual API, so it's completely binary compatible to what we get out when the compiler will be finally working. So the next thing we're planning to do is make the rates actually work, do some whole program analysis, optimizations. Right now we have a closure implementation of higher order functions. We plan to replace them by defunctionalization, and to deal with more hard real-time runtime environments. Right now we're using the Java Standard Edition, so there could be glitches at any moment when the garbage collector kicks in. We cannot guarantee that this won't happen. The take-home message is multi-rate high-order programming is really cool. You can do a lot of interesting things that crop up in audio, in scientific simulations, in engineering, and so on, because you can reconfigure signal processing networks dynamically as you go. So there are very simple applications like this tone. You can imagine that there are hugely complex applications. And many of the systems in practice cheat on the multi-rate and initialization part. They don't have any semantics at all for that, or they have very strange semantics that give you no guarantees. Reliability is a real problem for systems like Super Collider, Simulink, and friends. Okay, and I want to conclude just to demonstrate that this is really for real-time applications. There's just a little code. That's SIG code here. That's a sine wave generator. This is an ADSR envelope generator. Sorry, that's about it. And then we add, this is an overdrive component, like in a Marshall amplifier. And then we throw in some Java GUI and MIDI stuff that works out of the box, and we get something like this. Okay, thank you. Yes. So the question is about the staging when you when you take these cross-stage variables to be streams, then standard synchronization kicks in. So then X and Y must operate at the same rate, but F also operates at the same rate as X. So you can use each of these functions on one element only.